Okay, so today we are going to talk about two different types of reactions that are sort of opposites of each other: decomposition reactions and synthesis reactions. So this first one we're going to talk about is a decomposition reaction. Go ahead and write down these notes on your notebook. So you may be familiar with the word decompose from like crime dramas where they say, based on the state of decomposition, we can predict that her body has been here for like a week. Okay, this is a similar idea, but kind of a different principle. To decompose simply means to take apart or to break down. So what we're talking about is taking a compound and then breaking it into simpler components. Sometimes that means breaking it into the elements that have made it, or simply simpler compounds than the one that we started with. Now, you guys don't need to have a rules page because y'all are not going to have to predict products for these reactions. That would be hard, and we're not going to make y'all do that. Okay, so grab your worksheet where you have the charcoal chimney stacks demo, and go ahead and write down the equation for this reaction. All right, so here we have sugar, which we've given you the formula in this case because it's an organic compound. We're using its common name. We're going to give you that formula. Decomposes with a sulfuric acid catalyst. Catalysts. Now, if you recall correctly from the law of conservation of mass that we talked about in the reading passage at the beginning of the unit, catalysts are not part of the reaction. They are simply something that speeds it up or gets it started. So we put catalysts above the arrow because they're not really part of the equation, but they're certainly part of the reaction and something that needs to be noted. So we will put our sulfuric acid catalyst above the arrow. And then we have carbon as a product and water as a product. All right, so let's start with our sugar. We have C6H12O6. And then we have our arrow, and we need to put our catalyst on the arrow. So for sulfuric acid, we would ask ourselves, is the first element a metal? No, sulfur's not a metal. Does it end with the word acid? Yes, but it does not start with the prefix hydro. So we're gonna put an H because, oops, wrong spot, on the arrow, Ms. Crane. We're gonna put an H because all acids start with H. And then this is an ic acid, so we change the ending ic acid to ATE. That means we need to find the polyatomic ion sulfate on our polyatomic ions chart. So if you look on your polyatomic ions chart, sulfate is SO4, and it has a 2- charge, and that 2 charge is going to go on the hydrogen. So the formula for sulfuric acid would be H2SO4. Then it turns into carbon and water. We have an element by itself. So that's where we need to check the list of diatomics, our Hofbrinkels. Hydrogen, no. Oxygen, no. Fluorine, no. Bromine, no. Iodine, no. Chlorine, no. So it's not one of our Hofbrinkels, so we're just going to write it as carbon. And then we have water, which of course we all know is H2O. So that's our equation for the reaction we're going to do. Now we need to make sure that it is balanced. So I have 6 carbon on the left and only 1 carbon on the right. So I would put a multiplier of 6 in front of the carbon. I have 12 hydrogen on the left and only 2 on the right. So how do I make a 2 a 12? I would use a multiplier of 6. So I'm going to put a coefficient of 6 in front of the H2O. I have 6 oxygen on the left and I have 6 oxygen on the right, so this is balanced. Okay, so for this reaction, many times we will add a catalyst simply to speed things up. In this case, that's not why we're adding a catalyst. We are adding a catalyst because without a catalyst to trigger the reaction to begin, this is a reaction that would not happen. And you should know that because we all have sugar at home and it sits on our shelves and it doesn't do anything, ever. It never decomposes into carbon. Now, this particular reaction is a very, very slow one, even with a catalyst. So I'm going to go ahead and add my sulfuric acid catalyst very carefully. This is concentrated sulfuric acid, so it's pretty wicked stuff if you get it on your skin. So I'm going to do this very carefully. And we're going to watch it for about a minute, and then we're going to go back to our notes, and we'll come back to it at the end, at the end of class, to see what it looks like when it's done, because this is a pretty slow reaction. So we'll watch this for just a minute. Sorry guys, making you seasick. Camera fell. So you can just sort of see that we're starting to have just a little tiny bit of a color change. It's starting to go a little bit kind of a light yellowish color. All right, so we'll come back to this at the end of class and see how it's doing. All right, so the next thing we need to talk about is called a synthesis reaction. This is the exact opposite of a decomposition reaction, also a redox reaction. Here we are making or putting things together. So we take simple things, either elements or simple compounds, and we put them together into a compound or a more complex compound. So go ahead and record this in your notes. You can pause the video if you need to. All right, so the demo for this is the fireworks display demo. So let's go ahead and record this on our worksheet. Write down your equation. Here we have magnesium, and it is going to burn in oxygen. Okay? All right, we have magnesium, an element all by itself. So we got to check our list. Is it a Hofbrinkel? Is it on the diatomics list on your chart? So hydrogen, no. Oxygen, no. Fluorine, no. Bromine, no. Iodine, no. Nitrogen, no. Chlorine, no. All right, so magnesium is just going to be Mg by itself. Okay? Oxygen, element by itself, so let's go through our Hofbrinkels. Hydrogen, no. Oxygen, yes. So here we do have one of the Hofbrinkels. So oxygen is not going to be O, it's going to be O2. Now they didn't tell us the product here, but we can kind of predict that there's really only one thing that can happen, is that we form some kind of magnesium oxide. We got to put those two things together, those two elements together into a compound. So now let's re-crisscross our charges, because now that it's in a compound we have charges. Magnesium is a group 2 metal, so it's going to have a charge of 2+. Oxygen is group 16, so it's 2-. Those are going to cancel each other out, so we don't need any numbers here. All right, so that's going to be the equation for the reaction. Let's go ahead and balance this. I have 1 magnesium on the left, 1 magnesium on the right, so that's good. I have 2 oxygen on the left and only 1 on the right. So I need a multiplier to make a 1 and 2. So I'm going to put a 2 in front of the MgO. That distributes to everybody though, so that changed my magnesium to 2. So I'm going to need to change this magnesium to 2 as well. Okay. So in order to see this one really well, I'm going to turn off all my lights. I am going to advise you that you probably don't want to look directly at this, because it is one of the brightest reactions we have, and it can actually burn your retina. So we don't want to do that. So you kind of want to look off to the side. I'm going to light this on fire, and it's going to burn very, very brightly. So you want to kind of look off to the side so you're not looking directly at the center of the flame. Okay, and I'm going to come show you the product. Okay, so you can actually see right here, this shiny bit, that's some of our original magnesium. And then over here is this white stuff, and it's very brittle. It breaks apart into this white powder. That is the magnesium oxide powder. So you can see it's very dull, and it's kind of white and powdery, and very brittle. It breaks. So go ahead and record those observations in your data table.